Okay, everybody, welcome back to TARTLEcast. Thank you to everyone who has been an avid listener since day one, and to those who are joining us now today. You're coming into an interesting episode about innovative new algorithms advance the computing power of early-stage quantum computers.
Quantum.
What does quantum mean to people? I don't think people really know what quantum means. First,
I think people understand quantum computers if you're halfway techie.
Yeah, I think
you kind of get the idea of like
fast,
these super big, huge computers.
Yeah, you know, it's. Do you remember the days when IBM used to take up a whole room, like multiple rooms, like a whole floor of an office building, just for a computer to like crunch basic arithmetic
And it
on
had
punch
like
cards?
those little.
Yeah, exactly. Yeah, the tumblers and shit.
Yeah.
Well, the thing that's taking up the space now are the quantum computers. It's not that they need a whole bunch of electrical space. They need a whole bunch of space to cool something, right? So for these quantum computers, here's the whole idea. Today, when we go to compute something, it's a linear process. You can't compute multiple things at the same time. Yes, our processors are fast. Yes, it's quick, but it's printing 0 and 1 binary code one after another.
Mm-hmm.
With a quantum computer, it moves away from the linear aspect of computing where it has to do one thing before it does next. It has the ability to do two things at the same time. So instead of printing a 0 or a 1, it can print 0 and 1 at the same time.
Yes, that makes sense.
So its ability to do complications.
Complications. Yeah.
What the hell is the word? Calculations. Complex calculations. Its ability for it to do that is enhanced. The reason for this is because in physics, at a quantum level, when you're trying to actually understand like material science or things that are happening in physics, you have, things like spooky entanglement. Two things can be affected at the exact same time, but they're totally independent of one another.
Yes.
So the quantum computer is taking fundamentally these principles of entangling your zeros and ones and seeing how that can actually foster new calculations. So calculations that were attributed to understanding, string theory or the way atoms and electrons work, anything of that nature, is now being put into computers so it can be modeled appropriately at an effective speed. Because to do that modeling with our old way of computing is not efficient. Let's get into the article.
So this is what, I mean, when you talk about computation and calculations, I think this is what's really important. I watched a show on this scientist, and it's Yongxinyao, because I don't want to pronounce his name. Yeah, and his research partners, Amos Labs, use the power of advanced computers to speed discovery in condensed matter physics, which you talked about. This is what I think is really interesting. Current high-performance computers can model the properties of very simple, small quantum systems, but larger, more complex systems rapidly expand the number of calculations a computer must perform to arrive at an accurate model. So slowing the pace not only of computation, here's the difference, but also discovery.
Yeah, because the actions and reactions which happen at molecular levels or anything of the sort is very, very difficult to keep up with. In an atom itself, there's so much information just packed into one atom. Now, when I begin to combine these things to create certain molecular elements or bonds, the amount of information, like astronomical amounts of information, come out of those structures. So your discovery for finding new materials, say for instance, I want to create a new type of metal,
right?
But I want to essentially model how these two metals fuse together, right? Or I want to understand how these two chemicals fuse together. That's very difficult to do with our current computing systems. So if we can enhance that speed,
yes,
the discovery of which we advance our material science will grow tremendously. So the whole focus of this here is let's use these early stage quantum computers, taking up big rooms, keeping them super cold, to actually run advanced algorithms that can help us understand these large molecular groups.
Yeah, and I want to kind of get into a little bit of detail on the algorithm itself, these new algorithms that they're making. They tap into capabilities of existing quantum computers, we know this, and then tailor the number and variety of educated guesses, that's in quotation marks, educated guesses.
Yeah.
I mean, this is physics here. The computer needs to make an order to accurately describe the lowest energy state, because that's a problem. We're having issues with energy, as we do with, it's the same scenario with Bitcoin.
Yeah, when you're mining.
Yeah, when you're mining, yeah. I mean, you're using mass amounts of energy. But if it had if the lower the energy, like people don't understand this, and just with Bitcoin real quick, the lower the energy, the easier it is to hack.
Right.
The more energy there is, the more time it takes. So it's just a simple
It's a simple thing.
first
Like
principles.
if I want to create new material objects.
Right.
I want the lowest energy state. I don't want to have to run multiple nuclear power plants
Yes.
to fuse a new metal. Do you see what I'm saying?
Right.
I want to understand bonds at the lowest energy state. It's more. It's easier for humans to deal with.
Yeah, it's the lowest energy state in evolving quantum mechanics of a system. But this is cool with the algorithm. The algorithms are scalable, making them able to model even larger systems accurately with the existing current noisy, and what he's talking about noisy there is fragile and prone to error quantum computers and their new future iterations.
So here's what happens here. If you go to extrapolate an algorithm, whether in a predictive sense, educated guess, whatever you want to call you, as it gets to the fringes of the calculation, it breaks down. This happens a lot in advanced mathematics. So unless you tailor that back to a fundamentally scalable algorithm that aligns with how things in quantum mechanics happen at a fundamental level, now you have something scalable. So regardless of the size, it's efficient within that processing itself. It won't essentially deteriorate as it goes to the branches of the tree.
Yes.
Does that make sense?
Yes, no, that makes sense.
Great.
Yeah, and then he says accurately modeling spin in molecular system is only the first part of the goal. Said Yao. In application, we see this being used to solve complex material science problems.
There we go.
With the capability of these two algorithms, we can guide. So here's the outcome that they're hoping for. We can guide experimentalists in their efforts to control materials properties like magnetism, superconductivity, chemical reactions, and photo energy conversion.
Yeah. Okay. So here's some cool stuff to think about. If I can control magnetism, what does that mean? I can float around.
You can control the world.
You control anything, right? And they understand that. Why do you think they put that first?
Yes.
Second one, superconductivity. Superconductors help with battery capacitors,
Right.
storage, anything of that sort. So think about their list of priorities for the Department of Energy.
Yes.
We got to control magnetism so
Right.
that we can have anti-gravity. We need better storage capacities with our superconductors, all right? And then chemical reactions so we can create those new materials which would support those batteries.
Right.
And then the last one, photo energy conversion. So when our things are floating around in our charged ionosphere, sucking up electrons, we want to make sure that those materials are readily charged by what is readily available.
Yeah, and he says our long-term goal, so here we go, is to reach quantum advantage for materials, to utilize quantum computing to achieve capabilities that cannot be achieved on any supercomputer today.
Yeah. Here's the interesting part about the quantum. This is kind of cool. It's a very you can't put the cart before the horse here. But it's like I started with a stone tool and I'm like trying to cut stuff and it's not very good, right? Or in surgery, they used to use obsidian glass.
Yes.
And then they moved to scalpels.
It also kills White Walkers.
Yeah, it kills White Walkers. And then they moved to scalpels.
Right.
And then the scalpels moved to lasers. What is occurring here is that this early stage quantum computer is like having the early tool. You actually use it to make more tools. So once they can create new materials for the benefit of the supercomputer itself, once that gets to its lowest energy state, then there's no holding us back. It's essentially, that's the high bar we have to get over. Is that making sense?
Yeah, that makes 100% sense.
So what is the key here? Data and scalable algorithms. That's what it is.
And that's what everybody's working on today. But they say, the statement that they always say is not having the computing power, the computating power, and being able to harness that is the problem that's affecting it all. Like it's the hardware.
Yeah.
Like we can make the software to be able to scale to that level, but the hardware in and of itself is not there or available yet.
I'm getting a little deja vu from you right now. Was it a dream I had last night?
Of our long-term goals of quantum advantage with TARTLE.
Yeah, something is
having data algorithms that
are just astonishing. Yeah.
Well, I mean, we do first principles thinking. We go back to the source.
We go as far back as it gets.
That's as simple as.
Let's look at the basics. You know what I mean?
We don't need quantum algorithms.
Well, I think that's what they're learning
to
here.
share intent.
They've gone all the way out on the fringe.
Yes.
They've tried to apply their stuff, but they realize it breaks down, which means they have to fundamentally go back and take a real hard look at the thing that's supporting it all.
So if you're a business and you want to sign up for TARTLE, because I think this is really important. A lot of businesses don't understand they just are not introduced to TARTLE, one, or number two, they don't understand the capabilities
or the value of data
of what TARTLE can do for your business specifically.
Yeah. So
let's use natural gas industry. Let's just pick that.
That's a great example.
Yes.
So here's the cool part. Local natural gas company here in New Mexico, you could probably figure out who they are, sends out paper surveys. in the mail. And they hope that someone's going to take the time to diligently fill out this 15-question survey.
There will be one certain demographic that
will do that, and then mail that back to them. And then that's how they presume the safety education around gas pipelines is in the United States. By running that survey via paper that comes via junk mail, okay, to your mailbox, which you're going to throw away, they think that that is the key driver.
That's expensive too.
Oh, it's very expensive. Now, that has a very low response rate and also a huge carbon footprint, okay? Oil and natural gas, you already have a huge carbon footprint. Let's slow that down for a second and let's increase that response rate. So for them, digitize the survey to collect that data directly from the individuals who are participating in that region with oil and gas. Interesting. Oh, wait a minute. And they can embed educational videos to teach the person and then collect the survey data from it and then establish relationships to go back to them to say, now that this time has passed, let's ask you some follow-up stuff. The power of that for the decision makers in these corporations for actually educating on safety by federal law dictates that they have to do that, expands dramatically. And educating the public is number one. Number one, always. Because if they're not educated, people become agitated and they turn against you. So for your benefit as a business, whether you're in natural resources like that or you're Walmart, all companies are tech companies. So we ask you to take the step with TARTLE so you can establish those relationships with the people you serve.